Homework 3.3, Polynomial Division, Factor Theorem, Remainder Theorem, Video 6. Homework due Wednesday, May 27th, 2020 at 11:59 p.m. The following video will correlate to questions 11, 12, and 13 in the homework. This should be fairly transparent because this video is about something called the remainder theorem. And questions 11, 12, and 13 say, use the remainder theorem. Just a reminder, I'm not sure if I've told y'all this yet, but a theorem is a mathematical statement that has been proven to be true, so it's reliable. There are statements that are conjectures, meaning that people put them out there and it sounds true, but they can't prove it. And believe it or not, even though everybody thinks math is always cut and dry, this is right, this is wrong, that's a very naive perception of math. And there are things that people have conjectured in math that have not been proven true, but nobody can find an example to contradict them. A real simple one is called gold box conjecture, which says that every even number 4 and higher can be written as the sum of two primes. For example, 8 can be written as 5 plus 3, 20 can be written as 13 plus 7. They can't prove it, but nobody can find a counterexample to it. But I digress. So what is the remainder theorem? Well, as its name suggests, it has something to do with the remainder, and specifically a polynomial division problem when your divisor is x minus a number. It also works if it's an x plus a number, and honestly, this could be x plus a number if this number was negative, because minus a negative is positive. So it's really redundant to say the divisor must be x plus a number or x minus a number, because this captures both of them, understanding that this value here could be negative and minus a negative is a positive. So let's suppose we divide some polynomial function by x minus c, and we get a quotient which will be some other polynomial, but we'll just call it q of x, with a remainder of r. And it's important to point out here that if we divide by a first degree polynomial, the remainder will be just a number, because the degree of the remainder has to be less than the degree of the divisor. This is a first degree polynomial, so it has to have fewer than one x's, so it would have no x's. So it's always a constant if your divisor is linear. So if we got that, how would you check this? At the end of the previous video, we literally just did an example of checking the answer to a division problem. You check the answer to a division problem by multiplying what you divided by, so x minus c, times what you say the quotient is, and then add the remainder. And if it's the correct answer, the result should be the original dividend. So in other words, the checking statement here would be to show that the f of x was equal to x minus c times the quotient plus the remainder. So, big deal. Well, remember that x is a variable and we can let it equal any number we want. So what happens if x is equal to c? Well, let's put a c everywhere there's an x. We get f of c equals c minus c, that's just 0, times q of c plus the remainder. Well, this is 0, so 0 times this is still 0, and 0 plus r is just r. And we get f of c equals r. So what does that tell us? It tells us that the remainder of this division problem can be calculated instantly without knowing the quotient. It tells us that the remainder of the division problem is just equal to sticking this number into the function. And that would be the remainder theorem. The remainder theorem says the following. The remainder of some polynomial function f of x divided by some divisor of the form x minus a number equals f of c. So what it gives us is an alternative way to calculate a function without actually substituting the value into the function. All we have to do is run it through synthetic division. So for example, evaluate, let's say f of x equals x to the fourth power plus 3x to the third power plus 4x to the second power minus 5x minus 11 at, actually let's say this, if f of x equals all that, comma, evaluate f of 2. Now we could have answered, I could have asked you this a long time ago. This is just saying stick 2 in there, stick 2 into the function and work it out. But specifically using the remainder theorem. Well, all the remainder theorem says is the remainder of this division problem equals this. So what does that mean in the context of this? The remainder of f of x divided by x minus 2 is f of 2. Now why did I say x minus 2? Because the number that's going in here is what's getting subtracted. So let's set up this synthetic division problem. If we're dividing by x minus 2, what number goes in the box? The opposite of this number. So 2. Oh, wait a minute. 2 is the number we started with. Why didn't we just stick it in the box? Wait, we can't. Put this number in the box. Because when you build the factor, or on that later, the factor theorem, then when you pull the number out, you change its sign. So just stick this number into the box, run it through synthetic division. Top row, 1, 3, 4, -5, -11. Some people call this synthetic substitution because instead of substituting the 2 into the function, we're running it through synthetic division. Remember, the rules, the work is add, multiply by the box, add, multiply by the box. I'm going to go through this at the normal speed that I would. I invite you to pause the video and work it out on your own, but I'm about to buzz through it at normal speed for me. I don't even call out the moves. Add times 2, add times 2, add times 2. Numbers are getting big. Add times 2, add. Why am I freezing up? 35. So the remainder theorem says that this is the answer to f of 2. You don't believe me? Put 2 in there. Go ahead. Unless I made a mistake, it'll come out to be 35. Now I'm worried I made a mistake. I'll check it. Putting 2 here gives 16. Putting 2 here gives 8 times 3 is 24. 16 and 24 is 40. Putting 2 here gives 16. 40 and 16 is 56. Putting 2 here gives, putting 2 here gives -10. 56 minus 10 is 46. 46 minus 11 is 35. I want to do one more example of using the remainder theorem because this one, I don't want to say it was cluttered with the intro, but it was cluttered with building the remainder theorem. We actually not only wrote it, we kind of proved it when I said let x equal c. But in terms of executing the remainder theorem, it is so easy it's not even funny once you understand how to set it up. So let's just change this problem real quick. We'll change the function. Let's just make it a third degree polynomial. Let's say 2x to the third power minus 5x to the second plus 11x minus 39. And let's say we're going to evaluate f of -3 using the remainder theorem. All the remainder theorem says is if you want to evaluate a polynomial function at a value, instead of substituting it into the function, put it in the box as is, set up synthetic division, and at the very end you'll have the answer to your question. I think this is going to get a little large. Again, how fast it takes you depends upon how quickly you can process numbers. Calculator, feel free to use it. All right, add up the first column to get 2. 2 times the box is -6. Add to get -11. -11 times the box is 33. Add to get 44. 44 times the box is -132. Let me double check that. Yes. And when I add up the last column, I'll get -171. So that means if I plug -3 into the function, I'll get -171. And that's all the remainder theorem says. Don't send a number into the function, put it in the box and run it through synthetic division.